Here we're going to perfect our skills of taking basic integrals and using these basic integration rules, right? That formulas are here. And if you've made it this far, if you're lucky enough to be this far in mathematics, you probably know that practice and solving hundreds of problems is the name of the game at this point, right? So the more you solve, the better your skills are gonna get. So I'm gonna solve these integrals here. Some of them are very straightforward and some of them are more interesting. This one in particular is my very favorite. It's a very special integral to me. Anyway, we're gonna start with the first one here. I'm gonna get the u sub pocket. All right, so here goes the thinking, right? So you see that you have x and dx in the integral. That is somebody's derivative sitting there waiting for you. And whose derivative is x? It's x squared's derivative. So if you say that this is u, then you have du already there, and it's just going to be sin u du, and that's perfect. So derivative of that, which is du, is 2x dx. I like to also do an extra step to express exactly what I'm given, and I don't have 2x dx, I have x dx. Okay, that's du over 2. That's u, and you have sin u du. That's one of the basic rules of integration. So you look in your formula set and you see that the integral of sine is negative cosine u, right? There's 1 over 2 from here. Now you need to back substitute the variable that you started with, because the problem was given in terms of x. You need to have your answer in terms of the same variable, and that's the final answer. Let's box this. If you're unsure what integral of sine is, and you're thinking if it is negative or just positive cosine, you just have to take the derivative of your answer here, and you have to get sine. All right, now let's solve number 2. Here I'm going to rewrite this, and this is pretty much the basic rule. I just need to like tweak it a little bit and rewrite it just once so that it looks exactly like the basic rule. Okay, so now you go looking at this point and you find, so there's a variable square of minus, so that's arcsecant, right? At that point, you're done. And you can say that your a is 2. In this case. Okay, for this integral, number 3, you obviously have to use fundamental theorem of calculus, and this one is more of a real calculus because you're calculating area under the curve, which calculus was created to do. So here I'm going to get the graph. You put the function that you have in the integral. Unblur it, please. This function in Desmos, and then you see your bounds, so 0 to pi. Okay, so whenever you're taking integrals, area that is above x has a positive sign, and area that is below x has negative. So these areas seem to, when you're trying to do a ballpark, that's why you need to see the graph of this function that's in the integral, so that you can do a ballpark so that you know what answer makes sense and what doesn't. So these areas seem like they're equal, but they have opposite sign. This one has plus and this one minus. So probably the answer is going to be somewhere close to 0 in this case. I'm obviously going to use calculus and solve it and get an actual answer, but solving this without using calculus, assessing the area under the curve is very useful so that you catch your mistakes in the end. Oh, I'm going to do u sub here. I'm going to get that u sub pocket. Why do I know to do u sub? Anytime you have sine and cosine given to you in the integral, you realize that one of that needs to be u because the other one is du, because sine's derivative is cosine. So if you said that sine is u, then du is derivative of sine, and that's cosine x dx. Do you see how simple that is? That's exactly what you have sitting here. Same would be the case if you had secant and tangent. Those two are each other's derivatives in the integral, so those are always linked and come together, and sine and cosine are the same way. So when you have sine times cosine sitting there, it's a u sub. So this is going to be u squared du, and you can get new bounds, and you should, because whenever you're solving definite integral, in this case, this is definite integral when you have bounds, right? The answer is not going to be some function. The answer is going to be a number. It's going to be a scalar because you're calculating area under the curve. So you can just never go back to the original variable because you're not going to be having any variables in your answer. You're going to have a number. So upper bound, u sub pi, and then you put, wherever you see x, you put the upper bound, and that's 0, right? And then the lower bound, that's 0 as well. So now you take this interval, it's cube over 3. That's 0. The reason why this happened, this is actually a very interesting problem, but you'll find out towards the end of this course what happened in this interval, why this is 0. But ballparking it always helps. We kind of predicted it would be. Now this interval is extremely simple. It's just one simple step, and you need to remember that anytime you have x to the power of 1 and a constant, that is very, and then the whole expression is to some obnoxious power like 11 or even 1000, just realize that derivative of that is going to be 1 because derivative of x is 1 and derivative of any constant is 0. So this is going to be simply dx. You don't even have to do u sub whenever you have dx equal to du. You can kind of assume that you're doing u sub and treat this expression as one whole piece and then move it as if it was x or u. So 5 comes out of the integral. I'm still going to rewrite this as u sub just because we're only now starting. Okay, so I'm also going to bring this up so that you really appreciate that this is going to be a power rule where your n is negative 11, right? So you add 1, it's going to be negative 10 and negative 10, constant of integration. These get canceled. So the answer to this integral is, and then I'm going to back substitute, obviously. I'm going to have my answer in terms of x because that is the variable that the problem gave me. That's the final answer. Okay, 5th problem, and this is getting interesting. Lower bound is 0, upper bound is 2 over square root of 3, which is 1.15. So a very rough ballpark. We're calculating area under this curve from 0 to 1.15, right? So this is the area that I want. Well, obviously, without calculus, you can calculate that area, but I can't calculate the area of a rectangle, right, without calculus. And I can, obviously, I'm going to account for this, which is going to mislead me and give me a larger number than the actual, but it doesn't matter. I still want the ballpark. So here the width or the height is 0.25 and width is 1.15, right? So anytime you're multiplying by 0.25, that's dividing by 4. And 1.15 over 4 is 0.2875, right? Yeah. So we're expecting our answer to be somewhere 0.3, 0.4, 0.5, somewhere around there. So that just gives you a good ballpark. So we don't know what the exact answer is going to be. So here, this integral needs to be rewritten because it does not match any of the basic rules for integration just yet. So this does look quite similar to arctangent, inverse tan, right? However, there is no constant here. There is a constant squared here, but the variable part doesn't have anything there in the formula. But in our case, it does. So I need to bring this out, this 9 out of the parentheses. And the way that I can do that is I can divide this by 9 and then x squared. And if you're worried that I may have made a mistake, you can just put this back, right? And you see that this get canceled. So you have exactly what you started with. So you can be confident that we didn't make any mistake when you put it back. Now I'm going to rewrite it one last time just to make it look exactly like the formula. And of course, 1 over 9, that's a constant. So always bring constants out of the integral so that your integral does not look more cluttered than it needs to be. So square that, that's your a, right? And even whenever you have a complicated problem like this, I like to actually explicitly write out what a is so that I don't think too much and then I don't make a mistake. Okay, 1 over 9. And I'm going to take this integral at this point. So the formula goes like this, 1 over a. So if I divide 1 over 2 over 3, that's going to be 3 halves. Arctan x over 2 over 3, which is 3x over 2. That all of that is from 0 to 2 over square root of 3. Now, apply fundamental theorem of calculus. Arctan upper bound, which is over square root of 3, minus lower bound. And that's just 0, right? 3 over 2 times 0. So this term is 0. And the reason why, not, for example, arctan or arc cosine of 0 would not be 0, right? But arctan of 0 is 0 because remember what inverse trig is. It's like, what is this angle? That's what you're after, is 0. So tan of 0 is 0, right? And then here, these get canceled, and what you have here is square root of 3. So this is 0 because of that. And then this I will rewrite one last time. So again, arctan of what angle equals to square root of 3? Well, that's pi over 3, right? Because that's 60 degrees. because sine, remember sine has square root of 3, but don't think in degrees. When you're dealing with trig with integrals, all of those angles are in radians, so just forget about degrees in calculus 2 and switch to radians. So here you have 1 over 6 pi over 3, so that's pi over 18. Okay, let's check. This is the final answer. Let's check if this is close to our predicted answer, which was, I think, 0.2875, right? 1.15 over 4. Okay, so this is approximately 0.74. And it is quite close, because remember that we said that we were accounting for a little bit of an extra space here, so that's probably why we overestimated the area, but this is the actual answer. But pretty good, because if I got the answer to be like 7 or 1,000, I really know I made a mistake, so I'd go back and check. So these like solving things, definite integrals without using calculus, the way that people used to do it before 17th century, before Isaac Newton and Leibniz, is quite useful.